session number 10. In this section, I'm going to go through from question 26, okay? We're going to talk about some real-life situations just to get some of the terminology, because what I have found is a lot of people, when they're using or reading the questions, okay, they're finding it a little bit difficult to put the questions onto paper, because it seems to be a little bit of a thing here about how it is asked, right? Let us have a look. They say over here, an aeroplane can accelerate at 2 meters per second squared and decelerate at 1 meter per second squared for passenger comfort. Obviously, in an emergency, I'm sure it can really put the throttle and go up quicker, and it can also stop faster, but let's just say that. And for general aviation safety. Takeoff speed is given as 288 kilometers per hour and a landing speed 248.4 kilometers per hour. What is the length of runway needed to take off? What is the length of runway needed to land? Now, I know I say it over and over and over and over again, but make a little sketch, okay? Just so that you know what you're dealing with, right? What are we actually saying, okay? Let us have a look, first of all. Let us put over here, okay? And like I said, please, you don't have to really sort of go to town with a sketch. All we want to know is we've got our aeroplane. That's probably a bit too sort of simplistic, but we've got our aeroplane over here, right? And I think I used a 737, I'm not sure, but we've got that, right? Now, what have they told us? They have asked us, how long does the runway need to take off? Okay. Well, what they say is that the takeoff speed is given. So let's just put on what we know. The runway, we're going to start here and we're going to go to B. Okay. That is the length we need to take off. So physically, what are we saying? We are saying that an aeroplane sits here and then it starts accelerating and goes up into the sky, all right? Like I've said, think like the plane or the car or the truck or the person pulling things. Try and look at it as if you're playing with it as an aeroplane. You know aeroplanes, we don't just do that. You run them and they take off, okay? In other words, they need to get enough lift, okay, under the wings. Let's have a look. So at this point here, this means that the aeroplane is going to be doing this, right? At that point. Put in what we know. What is V initial here? V initial is equal to 0. What is V final? Hold on. That is the takeoff speed. 288 kilometers per hour, right? That's the speed at takeoff. The next thing is we say, right, what are we given? Acceleration, 2 meters per second squared. Right. Where do we go from here? What have we got? We've got V initial equal to 0. V final equal to 288. What's wrong with that? What do we have to do with it? The units are wrong. It's kilometers per hour. So we have to change it to meters per second. So what do? 288 kilometers per hour. I want to change that to meters per second. So what must I do? Well, I have to times that by 1,000 and I have to times that by 3600. There's my fraction, right? What do we end up with? We end up with 288 times that is 80 meters per second. So our 80 meters per second is there. Okay, we've got our 80 sec. Now, what's the next step? The next step is we are looking for what? Acceleration is 2 meters per second squared. What is the other one? The other one is delta t. The other one is displacement delta x. So what do? We look for a formula that's got the ones that we've got. And in this case, right, we are going to have the formula V V final squared is V initial squared plus 2a times delta x. And then what do? Then we put in what we're given. Well, Vf is 80 squared is equal, V initial is 0 squared. 2, acceleration is 2, delta x is that. So what are we looking for? Delta x. So therefore, 80 squared is going to be equal to 4 delta x. Therefore, we can come up with delta x to be equal to 1600 meters. 1600 meters. Okay. Straightforward. Now, the next thing they ask us for is, what is the length of runway needed to land? Well, let's now do the drawing the other way around. There we go. I'm not going to do B to A, but here we've got the aeroplane coming in. Okay. And the aeroplane is going to land over there. All right. It's going to land over here. There. At this point, the V initial is what? The V initial is the landing speed. 248.4. Okay, 248 point, I wrote meters per second because I'm thinking we must change it. Kilometers per hour. And the V final, well, it's landing. What is the plane going to do? I know this sounds really, and it almost sounds patronizing, but this is the way we've got to think about these problems. It's going to stop. So therefore, V final is going to be 0. Once again, A is 1 meter per second squared, I think, in this. So we put down, what have we got? V initial, 284.4 kilometers per hour, multiply by 1,000 over 3,600. I've already done it, and it comes to 69 meters per second. Think about it, that's pretty fast, eh? And V final is 0. A is equal to 1 meter per second squared. No, -1. Because we are decelerating. We're slowing down. Therefore, it's pretty much going to be the same formula. It's going to be V final squared is equal to V initial squared plus 2a delta x. V final is 0. V initial is as it's coming in. That's its beginning. Remember, we're splitting this into chunks of time, right? So V initial is going to be 69 meters per second plus 2 times -1 delta x. 69 goes across, squared, right? And if you work it out, you get -2 delta x is equal to 4761. The final little bit of calc we've got to do, therefore delta x is going to be equal to 2380.5. Okay, so now what we do is, if this problem was contained other bits, I'd put that answer back onto the actual calculation or the drawing itself. So I'm progressing, and each time I solve something, I put it up there. Where do we go from here? Well, first of all, obviously, the takeoff length is longer because the is shorter because the acceleration is higher. Okay? This is obviously for comfort, right? And I have used actual curves for the planes. Right, the next one, the number C. The plane encounters an emergency and has to land at an airport with a runway only 1,500 meters long. Calculate the deceleration. Woo. So here we've got it now. Okay, let me just move it up a little bit. We've got, in this case, we've got a runway. Now I draw it and I say I've only got 1,500 meters. Delta x. What is the velocity of my plane here? It's the velocity of landing. Right? Landing, and once again, V final must be 0. Okay. V landing, we know, was 69 meters per second. All right? And once again, your formula is going to be equal to V final squared is equal to V initial squared plus 2a delta x. V final 0, V initial 69 squared plus 2a delta x is 1500. All I'm doing is putting in what I've been given. 69 squared, and I solve for a, minus 69 squared divided by 2 times 1500. That gives me 1.586. Okay, yeah, minus 1.586 meters per second squared. Okay, that's that there. Now, okay, that's basically and we would say, okay, I can land there or I can't land there if we're in an emergency situation. In other words, can the plane accept a deceleration of 1.586 meters per second squared? Bear in mind, it's 50% more than the comfortable one. Okay. Now, question D. If the maximum emergency landing, D says 1.5, calculate the landing speed the plane needs to safely land at the new airport mentioned above. Now they've given a maximum deceleration. Once again, we do a little drawing. We say, cool. Okay, we now know that's, for being a purist, I'm going to say that it's like that. Okay, there we go. I've got over here, once again, I've got delta x equal to 1500 meters. That's what we've got. We've got maximum A is going to be minus 1.5 meters per second squared, and A is going to be in that direction, just that we keep our heads about us, right? Then we now know V final over here is 0. We need to know V initial. Therefore, V final squared is going to be V initial squared plus 2a delta x, and putting in everything we know, minus V, let's just, V final is 0 is equal to V initial squared plus 2 times minus 1.5 times 1500. Everybody see it? I've just substituted in. So therefore, minus VI squared is equal to that. And I work that out. That's going to be minus 3 times 1500. Therefore, VI squared, I'm just going to take it, is 67.08 okay, meters per second. Now I want that in kilometers per hour. So therefore, meters per second. And what am I going to do? I'm going to convert that. I end up with 241.5 kilometers per hour. You can see all we're doing is we just, the secret is to get that drawing, isn't it? Because once you've got the drawing, it gives you all the other bits and pieces. Okay, we've got that. The last one, how long does the aircraft need to take off and land at a normal airport with full-length runways? Well, how long does it need to take off? Well, what have they asked for? They've actually asked for delta x. Taking off, we said what? V initial is 0. V final was going to be, I think, our 80. Right? Remember that from the question number 1? And how long does it take off? No, they didn't ask us how much. Sorry, they didn't ask that. They asked how long does it take? Okay, so they're asking for time. Okay, my bad. We've got an acceleration this way of 2 meters per second squared. And what do we say? We say, right, we've got V final equal to 80 meters per second. V initial equal to 0 meters per second. Why? Because it's stationary at the end of the runway. waiting for its chance to take off. The next question, we've got A is equal to 2 meters per second. Therefore, you'll go V final is equal to V initial plus AT. V final, AT, equals 0 plus 2t. T is going to be equal to 40 seconds. All right. And the next one, I know it feels quite long, doesn't it, when the aeroplane is taking off. The next one, they are now saying it slightly differently. We're saying that, in other words, it's landing. So V initial here is going to be our landing speed, which is 69 meters per second. Delta X is not an interest. We want T. And V final is equal to 0. Therefore, V final is equal to V initial plus AT. V final is 0. And A in this case is that way of minus 1 meter per second squared. Therefore, we can say V initial is 69 is equal to, plus minus 1 T. Therefore, T is going to be 69 seconds. Okay, that's the landing of that one. Have a look now at question number, this is question, that was question 26. Let us look at question 27. A car is traveling at 80 kilometers per hour towards a stop street. Okay, these are typical questions. I mean, essentially, if you go and have a look, this is the kind of question that gets asked, right? Because remember, there's only a certain amount of ways that a question can be asked. A car is traveling at 80 towards a stop street. Okay, if it's 250 meters away and can decelerate at 5 meters per second squared, just let me put on my squares here, will it stop in time? This is braking distance, isn't it? Okay, A. So we're looking at question 27A. Question 27A. Now, this part is Steward Drawing. Right, here we go. Here is my stop. Is there, correct? And let's put in what we know. We know it's 250 meters. And we know we've got a car at this point. Okay, I know I'm not an artist. And our car is traveling this way with a velocity equal to 80 kilometers per hour. Okay, spot the mistake there. I've got to change that to meters per second. This is V initial, isn't it? All right. Car is traveling at that towards a stop street. If it is 250 meters, can decelerate. So now they've also told me acceleration is minus 5 meters per second squared. Now, please bear in mind, in a lot of these cases, you could have taken a different formula and got the same answer. It's not a necessary given fact that you have to go in route A or route B. Some are just a little bit longer, but you're going to come to the same result at the end of the day. Here we go. I just want to get this one. Okay, there we go. And we say the last one, V final is equal to 0. Well, let's have a look. Let us work out, right, how many meters does it take to stop? Well, using this, so we're going to use what we've got. Okay, so let's work out V initial. First of all, is 80 is going to be equal to 22.22 meters per second. Matter of interest, that's quite a long way, isn't it? In 1 second. Just go and have a look how far in 1 second a car travels if it's doing 80. Pretty far. Now, V final equals 0. A is equal to minus 5 meters per second squared. Well, let's work out delta X. Okay, delta X will tell us how far it takes to stop. Right, so let's have a look. We need a formula. Okay, V final squared, V initial squared plus 2A delta X. Same formula again. I'm now going to use this here. Here we go. V final 0, V initial 22.2 squared plus 2 times minus 5 times delta x. Straightforward. What did we say? We're just putting in what we know. We're looking to see, and here's the nub, we're saying, well, we've got 250 meters. How? Because they asked, will it stop in time? The time is a little bit of a red herring, trying to make you look at time. Okay, but the reality is, how long, what distance does it need to stop? So we say, cool, we've got that. If you go and you work it out, that becomes minus 22.2 squared is equal to minus 10 delta x, and we get delta x is equal to, over here, 49.37 meters. This is known as the stopping distance. It's known as the stopping distance, isn't it? The stopping distance, excuse me, uses maximum acceleration possible. Except I should have said negative acceleration possible. Let's have a look the other way. Okay, the other way is I could have said, well, what acceleration do I need to stop given the 250? Well, or what deceleration, right? So I would have said v final squared, v initial squared, plus 2a delta x, okay? V final is 0. V initial is still 22.2 squared, plus 2 times a times 250. So now we're working out what is the acceleration that we are stopping with, isn't it? Here's my car. I really need to get some of these cars. Here it's coming, and now I'm saying, okay, I'm putting the brakes on, but I'm looking, I need to stop 250 meters ahead. So if I brake evenly, okay, what is the deceleration? And I end up with, it comes out to be 0.987. Okay, approximately 1 meter per second squared. Okay, which means it can easily stop. All right. So therefore, 1 meter per second is actual braking. Negative acceleration, right? The maximum being 5, minus 5. We therefore obviously will stop well in time. The next question is part, would be the minimum stopping distance. Well, the minimum stopping distance is let me just write it down, B, minimum stopping distance equals what? Is the braking distance. Okay? Which I've worked out above. Distance. Okay? There. And that was, I think it was 49.37 meters. Right. Well, then we say, how long can the driver travel at 80 before he must apply the brakes to stop? Right. Let's just, because now this is going to have, this is two parts to the question. He is over here. Okay. This is where we are now. We are traveling along in our little car. Okay. And we see a stop street over here. And we know that delta x is equal to 250 meters. That's where we are. Now we've said, right, what are we going to do? We're going to carry on driving. I'm just going to change the color. We're going to carry on driving at 80 kilometers per hour until the last second. And then we're going to, in this piece, we're going to brake at maximum. This is one of those, isn't it? Oh, we know we need to stop, but we do that. Okay? This is your screeching tires and hoping like crazy that this is actually going to work. Because if you miss it, you're going over the line of the stop street. Okay? Or even worse, you're going to hit the person who's already stopped there. So therefore, this is the kind of this is kind of like very aggressive, very irresponsible driving, isn't it? And they say to us, right, we say, okay, what do we know? Well, we know over here that this distance here, okay, we know that this distance here is going to be 49.37 meters, isn't it? So therefore, the distance left, okay, the distance left is 250 is equal to 250 minus 49.37, and therefore it's 200.63. So I'm going to travel 200 meters out of the 250. Then at that point, I'm going to hit the brakes and hope that we stop. Obviously, if the road is wet, not going to stop, are we? We're going to slide. Okay, I know if you've got ABS brakes, they do that a rapid braking system. Fair enough, possibly, but that's just a hypothetical situation, right? That's somebody who's chancing up to the last minute. The next question, the last one of this, what is the total time taken, okay, in the question, right? They want to know what is the total time taken in the question, right? How much time can you see? Just make another page and then just page it down slightly so that I've got my drawing that I want to work with. Just gets here. Okay, let's just have a look. So what have we got? We've got this piece of the time, delta x equal to 200.63 meters. Velocity here, 80 kilometers per hour. So it's traveling at the constant speed there. Then over here, my V initial and VF is going to be 0. V initial here is the 200. V initial over here is not the 200, the 80. So the initial velocity there is the 22.22, isn't it? And over here, the initial velocity is 22.22. Can you see I've split it into constant velocity piece and then a deceleration piece? That is what we do. You'll see it in the energy ones again. We split them up into, in this piece, we're doing this, and we deal with that. Then we move on to the next piece. Here we go. We say, righty-ho. Therefore, what am I looking for? I am looking for how far did I go, right? So I'm going to look at it as delta x, okay? Delta x is equal to VI times t plus a half AT squared. What is the acceleration in the first piece? Let's go back, shall we? Okay. Let's put in green. Acceleration here. Well, the acceleration here is minus 5 meters per second squared, is it not? The acceleration here is 0. It is traveling at a constant velocity. We are not accelerating. We're not going faster or slower. We are staying at the same velocity. Therefore, A is 0. Fundamentally, we're then going to say delta x, we know, is 200.63 must be equal to V initial times time, 22.22 t. This is the old formula. I don't really want to use it. Speed is equal to distance over time, isn't it? Essentially. Okay. Time is going to be equal to. Okay. So what have we got here? We say right, therefore, the time for the first piece is going to be 9.03 seconds. 9.03 seconds. That is the time traveled in the first piece. So let's go back to our drawing. We say, right, over here then, this time here equals 9.03 seconds between there and there. Now the next piece is we want the time on that side, don't we? We want the total time taken. Right. Well, now let's have a look. The time to break. This is breaking time. Okay. Once again, V final is equal to V initial plus AT. And we say V final is 0, V initial 22.22 plus minus 5T. Therefore, T comes out to be, in this case, minus 22.22 over minus 5, which is equal to 4.44 seconds. Right? So let's go back to our thingy. 4.44 seconds. So how long did the whole escapade take us? It took us basically 9.03. Right? Total time equals 9.03. This is the constant velocity time. Plus my braking time, 4.44. This is braking, which is going to be equal to 13.5 seconds. Okay? I rounded it off. 13.5 seconds. Okay? Bear in mind they will tell you whether you can or not. Okay, I've gone over again, but we did take our time through it, and hopefully we went through the concepts well enough. Okay, thanks for watching that one. The last one will be the question 28, which is the balloon, and question 29, which is the energy problem that I'm going to do. Okay, so please go back and look at that problem. Go through it and always split these things. Remember when we did that graph one, the graphs of motion? We split it up into the sections, didn't we? That's how we do these. Little bit by little bit by little bit, and as you get your answers, you go back and write them on your diagram. The diagram is absolutely fundamental to this process. Cheers, I'll see you in the next one, which will be the last one for this series of exam prep. Bye.